Section: Introduction. In this section, we discuss the growing trend of using large language models, LLMs, through chat interfaces to respond to user queries. We achieve this by pre-training models on vast amounts of text from the web and then fine-tuning them on smaller sets of instruction response pairs. We can create these instruction tuning datasets in several ways: through human annotation, converting existing texts into instruction response pairs, or distilling knowledge from other models. Each method has its pros and cons. While human annotation can provide strong baselines, it is challenging to scale due to the need for human input. The effectiveness of the first two methods also relies on filtering out noisy data. In contrast, distillation is more cost-effective and scalable, but it may not always lead to significant improvements in capabilities. We recognize that having high-quality and diverse data is essential for effective instruction tuning. Given the wealth of information available online, we explore generating instruction response data using back translation, which has shown promise. Specifically, we analyze the Clue web corpus for relevant text segments, train a model for instruction generation using Open Assistant data, and create instructions for these segments. However, this method depends on high-quality data from Clue Web, which is a paid resource, and requires specific rules for parsing HTML into structured responses. In our work, we also utilize the instruction back translation technique but aim to make it more accessible and scalable. We use pre-processed documents from a large open-source corpus, DOLMA, to generate instructions through back translation. Our findings indicate that the quality of our generated instructions is comparable to those derived from Clue Web. To address the absence of manual structuring rules, we experiment with using an LLM to rewrite responses based on the generated instructions and the original web text. This approach helps us avoid overfitting to an LLM's knowledge. We present our pipeline, termed back-and-forth translation, and demonstrate that fine-tuning the Llama 2 to 70B model on our instruction response pairs improves performance compared to previous back translation data and other distillation datasets. By prompting a model to rewrite responses based on initial texts from DOLMA, we create a response distribution that blends the original web text with distilled outputs. Fine-tuning on these rewritten responses outperforms fine-tuning on distilled responses for the same instructions. We also provide insights into how instruction back translation and response rewriting influence the quality of instructions and responses, particularly in comparison to existing data generation methods. Overall, our results suggest that back-and-forth translation is an effective way to generate diverse and high-quality instruction tuning data, leveraging the strengths of aligned LLMs. In the following sections, we will detail our pipeline and the background of instruction back translation, inspired by previous work that fine-tunes a base language model on seed instruction response pairs to create a backward model for generating instructions. This model is used to extract candidate responses from web corpora, which are then augmented with corresponding instructions. The final dataset consists of high-quality examples, demonstrating the importance of careful curation in achieving performance improvements. Section Summary. In this section, we discuss our approach to generating instruction response pairs using back-and-forth translation, which leverages a large open-source corpus to create high-quality instructions without relying on costly human annotations. Our method improves the performance of fine-tuning large language models by ensuring diverse and less noisy data, ultimately enhancing the quality of instruction tuning datasets compared to traditional distillation methods. Section: The Rewriting Process. In this section, we discuss the rewriting process. A significant limitation of earlier research is the scarcity of high-quality candidate responses. We utilize ClueWeb as our source for unlabeled responses, focusing on well-linked websites like Wikipedia and popular news sites to ensure quality control. However, ClueWeb has some drawbacks. It requires paid access, and the text segments are extracted from raw HTML, necessitating specific preprocessing that may still yield suboptimal responses. To address these issues, we eliminate data access restrictions and preprocessing by using clean documents from the open-source DOLMA corpus for our initial web-scraped responses. These documents are pre-extracted, meaning they have had all HTML removed, but they may still contain redundant information and could benefit from improved content presentation, such as being organized into paragraphs. Therefore, we employ a large language model, LLM, to enhance these documents, making them more akin to responses from AI assistants. This step is labeled as 3. Rewriting in our figure. We condition the rewriting process on the initial text from DOLMA and the corresponding back-translated instruction. We prompt an aligned LLM, specifically Llama 2-70B chat, to rewrite the response to enhance its quality. The complete prompt details can be found in the appendix. Typically, we apply rewriting to pairs that have passed our filtering stage, but we also experiment with rewriting any pair, even if the forward model identifies some misalignments. Overall, we find that the rewriting step is more effective than filtering, although using both provides complementary benefits, which we will discuss further in a later section. For our experiment setup, we source the initial web-crawled responses from the common crawl subset of DOLMA v1. This subset has already undergone quality and content filtering, as well as deduplication. We also filter out documents that are close to exceeding the context length of LLAMA2, which removes about 25% of the common crawl subset. We focus on the head split, which contains documents with the best perplexity scores, as our preliminary experiments indicate it yields better candidate responses than the middle split. For the seed data to train our forward and backward models, we follow previous work and select 3,200 examples from the Open Assistant dataset, specifically from the first turn of each conversation tree. This seed data consists solely of high-quality English language responses, ranked as the best by human annotators. We fine-tune a Llama 2-70B base model on this seed data to create the forward and backward models used in our pipeline's initial steps. The rewriting step defaults to using Llama 2-70B chat, but we also test a smaller model, Llama 2-7B chat, and the forward model from the second step for rewriting. However, we observe that these alternatives produce lower quality outputs. For performance evaluation, we fine-tune both the 7B and 70B versions of the Llama 2 base model on the resulting instruction response pairs in a supervised manner, with specific hyperparameters detailed in the appendix. In our evaluation, we prompt the fine-tuned Llama 2 model to respond to 805 questions from the Alpaca Eval benchmark and report its win rate against Text DaVinci 003, as assessed by the GPT-4 model. We also use a length-controlled win rate evaluation from Alpaca Eval 2.0, with more details available in the appendix. Performance on other NLP tasks is also included in the appendix. For our baselines, we compare our method against several fine-tuning data sources. OpenOrca contains outputs distilled from GPT-4 for FLAN tasks, converted from existing NLP datasets using crafted templates. Shared GPT data comes from users sharing their conversation logs with ChatGPT, and we only use the first instruction and response from each conversation. Clue web responses are parsed from HTML files without rewriting, and instructions are generated through back translation. After preprocessing and curation, previous work produced a total of 41.8K instruction response pairs. Self-instruct generates instructions, inputs, and outputs using GPT-3, starting from a small set of seed tasks. Alpaca GPT-4 includes responses distilled from GPT-4 for instructions from the Alpaca dataset, which aims to improve upon the self-instruct framework. We note that, except for the first two sources, the remaining baselines use synthetic instructions, and most datasets, other than ClueWeb, derive responses from various existing LLMs. We utilize these GPT-distilled datasets solely for research and non-commercial purposes, serving as competitive baselines for our method. Section Summary. In this section, we address the limitations of previous methods by utilizing the DOLMA open source corpus for initial web scraped responses, which eliminates data access restrictions and preprocessing challenges. We enhance the quality of these responses through a rewriting process using the Llama 2-70B chat model, demonstrating that this approach is more effective than filtering alone. while also detailing our experimental setup and evaluation against various baselines. Section: Fine-tuning results. In this section, we validate the effectiveness of our data generation method by comparing the performance of Llama 2 models fine-tuned on our data against those fine-tuned on other datasets, using the same number of instructions. For the 7B scale, we set the sample size to 12.8K and compare the fine-tuning of the Llama 2 to 7B base model on our back-translated and rewritten data with other common baselines. We describe our data variations in detail. 1. DOLMA plus filtering. We gather initial responses from the DOLMA corpus, generate instructions through back translation, and filter out pairs that do not score at least 5 from our forward model, meaning they are not well aligned. No rewriting occurs here. 2. DOLMA plus rewriting. We take candidate responses from DOLMA, generate instructions with back translation, and rewrite the responses using Llama 2 to 70B chat, without any filtering. 3. DOLMA plus filtering plus rewriting. This involves all steps of our pipeline. We find that our filtered back translation data outperforms similarly constructed data from previous work. Our best dataset, which includes both filtering and rewriting, shows a better win rate than all other baselines. Notably, fine-tuning on rewritten responses from unfiltered pairs is more effective than on filtered but unrewritten responses, indicating that rewriting significantly enhances the quality of instruction tuning data. For the 70B scale, we also fine-tune the Llama 2 to 70B base model on various back translation data variants. Our approach, which includes response rewriting, overcomes the limitations of previous work that relied on high-quality text from the initial web corpus. We generate 51.2K instruction response pairs. While back translation and filtering alone yield a model that slightly lags behind previous models, adding rewriting allows us to surpass them by 3.6%. Similar to the 7B scale, we observe that fine-tuning on rewritten responses is more effective than on filtered responses that have not been rewritten. Next, we analyze the quality of rewritten data. We explore how the outputs from rewriting differ from those obtained through distillation. Rewriting aims to improve response quality based on initial web-crawled responses and back-translated instructions. We question whether rewriting utilizes information from the raw text or simply distills knowledge from Llama 2 to 70B chat. Using the MAV score, we measure the differences among 3 response sets: initial web-scraped responses, rewritten responses, and distilled responses. The MAV score, which ranges from 0 to 1, indicates similarity in text distributions. We find that distilled responses from the same distribution show a high MAV score, while initial responses from DOLMA and distilled responses differ significantly. Rewritten responses show some similarity to distilled outputs, but there remains a notable gap, suggesting that rewriting is distinct from distillation. We also compare the performance of fine-tuning on rewritten versus distilled data. Feeding 25.6K instructions to Llama 2 to 70B chat for direct answers yields lower win rates compared to fine-tuning on rewritten texts. This demonstrates that rewriting generally improves response data quality, likely due to the incorporation of diverse information from web-scraped texts. Section Summary. In this section, we validate our data generation method by comparing the performance of Llama 2 models fine-tuned on our back-translated and rewritten data against other datasets, finding that our approach, particularly with both filtering and rewriting, significantly outperforms previous methods. We also analyze the quality of rewritten data, demonstrating that it is distinct from distilled responses and leads to better model performance, indicating that rewriting enhances the diversity and quality of instruction tuning data. Section: Measuring instruction quality empirically. In this section, we aim to evaluate the quality of instructions from various datasets by standardizing the response distribution to outputs generated by the same model. Specifically, we randomly select 12,800 instructions from our back translation data, both filtered and unfiltered, as well as from each baseline dataset mentioned earlier. We discard all existing answers and input each set of 12,800 queries into the Llama 2 to 70B chat model to generate new responses. We then fine-tune a Llama 2 to 7B model using pairs of instructions and their corresponding new responses, and we assess the performance of the resulting model using the Alpaca eval win rate. Our findings indicate that filtered back translation instructions, such as those from Dolma or ClueWeb, perform better than other synthetic instruction generation methods like Alpaca and self-instruct. However, synthetic instructions still do not match the quality of human-written instructions obtained through user interactions with ChatGPT. Additionally, instructions created by transforming existing NLP datasets, like OpenOrca, do not show strong distillation performance, likely due to their limited and repetitive task types. To measure diversity, we analyze the number of unique trigrams across different instruction sets while keeping the data quantity constant. We observe that our instruction set, back-translated from Dolma, is more diverse than other synthetic sets, including ClueWeb, Alpaca, and self-instruct. Nonetheless, there remains a notable diversity gap between model-generated and manually crafted instructions, such as those from OpenOrca and SharedGPT. We also note that human-written instructions tend to be significantly longer than synthetic ones. To investigate how length affects instruction quality, we conduct an ablation study by filtering out longer instructions from SharedGPT and randomly sampling 12,800 shorter ones. This results in a shorter version of SharedGPT, which we find still outperforms back-translated instructions, suggesting that human-written instructions are generally of higher quality, regardless of length. For complexity, we utilize the ins-tag complexity metric and the ins-tag public tagger, which is a Llama 2 to 7B model fine-tuned on tags generated by ChatGPT. We measure the average number of unique tags found in instructions and responses from each dataset. Our Dolma back-translated instructions show higher complexity than most previous instruction sets, including those from ClueWeb and OpenOrca, while human-written instructions from ChatGPT interactions yield the highest average number of tags. We apply the same diversity analysis to response data and find that the initial web responses from Dolma are significantly more diverse than outputs distilled from existing models like ChatGPT, GPT-4, and GPT-3, as well as web texts from ClueWeb. Although the rewriting process slightly reduces the information diversity of these web-scraped responses, they still remain more diverse than distilled outputs. This highlights the importance of incorporating web sources in our data construction to foster greater diversity in instructions and responses compared to solely relying on existing language models. Lastly, we analyze the complexity of responses from our pipeline, both with and without rewriting, using the average number of semantic and intention tags as a complexity measure. Our initial web-scraped responses from Dolma exhibit the highest complexity, while rewriting generally decreases this complexity. However, our rewritten responses still maintain a higher complexity than most existing response data, which is typically distilled from high-performing language models. We also provide an analysis of instruction and response lengths as an additional quality metric, with further details available in the appendix. Section Summary. In this section, we empirically measure instruction quality by distilling responses from a unified model across various datasets, finding that filtered back translation instructions outperform other synthetic methods but still fall short of human-written instructions. We also assess diversity and complexity, revealing that our back-translated instructions are more diverse and complex than synthetic ones, yet human-written instructions consistently demonstrate higher quality overall. Section: Related work. In this section, we discuss related papers that either create new instruction tuning datasets or suggest methods to enhance existing ones. We can find more detailed reviews in other sources. We start with human-crafted data. Datasets like Open Assistant, DALL-E, and SuperNI consist entirely of conversations generated and annotated by humans, covering various topics and NLP tasks. However, these datasets are often small because manual annotation is costly. Some studies repurpose existing datasets instead of asking humans to create questions and answers. For instance, FLAN and natural instructions convert inputs and outputs from over 60 NLP tasks into instruction tuning data, facing similar scalability challenges as human annotated datasets. Next, we look at synthetic instruction generation. Instead of relying on manually written instructions, some papers propose methods to automatically generate large amounts of instructions. Our work draws inspiration from a back translation technique that fine-tunes a language model specifically for instruction generation, then uses it to enhance text segments from the web with relevant instructions. This method aims to create more diverse instruction tuning data, especially for less common cases. Another related work, Longform, uses a similar strategy for instruction generation. Our approach differs in that we generate instructions separately using back translation and then improve existing responses with a language model. We achieve better performance with significantly less data, generate more data overall, and provide deeper insights into the quality of our instructions and responses compared to other datasets. We also discuss distillation, a common method for generating instruction tuning data. This approach mimics the capabilities of powerful language models, like GPT-4, by feeding them queries and using their outputs to fine-tune other models. Datasets created this way include ShareGPT, OpenInstruct, Alpaca GPT-4, and UltraFeedback. Regarding the quality of instruction tuning data, some previous work has examined the traits of high-quality data and suggested curation techniques. For example, Lima collects 1,000 fine-tuning samples through internet sourcing and human annotation, demonstrating that strong performance can be achieved with a small dataset. Similarly, other studies show that fine-tuning on a small subset of an original dataset can yield performance improvements. Some works find that selecting the longest responses from existing datasets provides a strong baseline, regardless of the preference for longer texts. UltraInstruct and Orca enhance instruction complexity through manual prompting. In our discussion, we propose a method called instruction back-and-forth translation, which combines instruction back translation with response rewriting. This approach leverages the diverse information available online and the quality of model annotations while allowing for scalability due to the vast web corpus we use for initial responses. Looking ahead, our findings open up several interesting future directions. One specific question is whether applying existing curation techniques, like quality filters, to our synthetic instruction and rewritten response pairs would improve performance. We also aim to scale up our data generation process and explore how rewritten data impacts the pre-training phase, especially in light of concurrent research on paraphrasing pre-training data into question-answering formats. We acknowledge some limitations in our work. Our findings are based on a single model family, Llama 2, and our pipeline focuses on general-purpose English instructions, with limited coverage of coding or science-related tasks. However, we believe our method can be adapted for more specialized domains, such as by gathering texts from Stack Overflow and generating instructions and responses using Code Llama. Finally, we consider ethical implications and potential risks. Sourcing response data from the web may affect the factual accuracy of the fine-tuned model and increase the likelihood of generating incorrect information. These risks also apply to the response rewriting process. Future work could involve additional steps to verify the quality of the information in the responses and ensure it aligns with the model's existing knowledge before using the data for fine-tuning.